All right, this is lesson 1/4, 1-4, and the title is Continuity at a Point. Continuity at a point. All right, so let's set up our Cornell notes. We draw our line, and our first category is continuity of polynomials. So I'm going to abbreviate here. Continuity is going to be cont of polynomials. All right, so first thing, what does it mean to be continuous? I'm going to put that in the left. So continuous, abbreviating, of course, equals, this means that there are no holes, there are no breaks, gaps. These are all bad. These will make it discontinuous. There are no gaps or vertical asymptotes. I will write that out. I'm going to call it VA, and hopefully you'll remember that for the rest of the year. VA, this guy right there, is vertical asymptote. So all of these things cannot happen in order for it to be continuous. Let's look at some examples. So we need to make 4 graphs. 1, 2, 3, 4. You can make them a little bit bigger than that, I guess. Let's label this one linear. Let's look at quadratic. Let's look at a cubic. And, I don't know, just a general polynomial. I might have to abbreviate that. IAL. What am I doing here? IAL. Polynomial. Okay. So what do these graphs look like if you just saw the picture? So linear just means a line, not a vertical line, but some line with a slope, hopefully. Quadratic, this is a U shape. It can be upside down or like normal, or right side up. Not really normal. Cubic, it can switch directions. Woo! And polynomial, it could have like x to the 9th power. It could switch directions a bunch of times. Woo! It can go all the way over there. The note on all of these is that these are all continuous everywhere. So continuous everywhere. I'll do arrows to each of these. Each of these is continuous everywhere because they don't have any holes, breaks, gaps, vertical asymptotes. So the main takeaway from this little section, and I'll do this in a little star, maybe I'll even change it to red, is that polynomials are continuous everywhere. Everywhere. All right. So that's that section. Let's go to another section. I can squeeze it in on this slide. I'm going to call this continuity of ratios. So let's call this continuity of, I'm just going to do capital R, capital A, capital T, and that's going to stand for ratios. Ratios. It'll be our little abbreviation so we can go faster. So ratios. Ratios can have a lot of weird things happening. Usually 3 different types of things. So let's make 3 graphs. And we just need words under them, so you don't need that much more room. So let's look at one thing that could happen. Let's see. You could have a graph. Ooh, I should probably change the color here of the graph to make it look uniform with the top graphs. You could have a graph that looks like this, that comes in like that. So at this point right here, that is a discontinuity. I'll even write it down here. Discontinuity. And if I label this point, I don't know, -3, it's a discontinuity at, that's that symbol because I don't like writing AT, at x equals -3. All right, let's look at another example. Stay in red here. Let's look at a vertical asymptote. So maybe something that comes like this. All right, so at this point, I'm going to call this point 2. I'm going to call this a vertical asymptote. So this point, there is a vertical asymptote. Remember, I'm abbreviating it VA, just like we did up here. A vertical asymptote. This is also just known as a discontinuity, or discontinuity. And you can say again at x equals 2. So there's a discontinuity when I get to the value of x because there's no value of y. And the last thing is a hole. So what is that going to look like? So draw a line, and then all of a sudden it breaks, and then the line keeps on going. So that at this point x, let's call him 3, there's a hole. That's hull. I don't know what's going on there. That just means that there is no value at that point. And this is kind of our terminology, hole. It wouldn't be really accepted for AP testing, although if you can't think of anything, you can just think of it as hole. But the technical word here is, what am I writing here? Discontinuity. Oh my gosh. Come on now, Mr. Sindel. So there's a hole in it. So we can use the word hole to describe it in our class. So the main thing here, unless the denominator is a number, in fact, don't even think about that. Let's just say this one key thing. Change color to let you know that this is a key thing. And then we're done writing for this slide. Ratios, or RATs, because we are abbreviating everything in this class. RATs, or ratios, are never continuous. Maybe even underline never, just to make that more pronounced. Alright, let's get this new slide set up. Whoosh. Okay, so this section is going to be called continuity of polynomials. So continuity of piecewise, not polynomials. I take that back. Piecewise functions. Piecewise functions. All right. So in continuity of piecewise functions, so this is the continuity test. This is probably the most important thing that I can teach you from this lesson. So proving continuity. There's going to be proofs in here, but this one is pretty easy. And this has another name. It's also called the continuity test. Continuity test. This is how I'm going to be referring to proving continuity. I won't say do the proof. I'll say use the continuity test. So this is the most important thing, I think, for today, and that is this. So that the limit of a function f of x, come on, that's supposed to be next, as x approaches some point c or a, I don't know, what do you want to call it, from the left, so the minus is there, needs to be equal to the limit of that same function as x approaches the same point from the right, and that also, all three of these conditions need to be met, needs to be equal of the value at that point, at c. And if this seems a little bit hard to get your head around, don't worry, we're going to be doing some examples. So another way of thinking about this is that the left limit must be equal to the right limit, which must be equal to the point. Remember, c is going to be the x value, and then f of c is the y value, so it's x comma y. That's just a point. So this is the most important thing. I would box this, I would do special things to it somehow in your notes, make this stick out. All right, from here we have some examples, and by now you should be on the second page. I just had to go to my second page, so this next section I'm going to call examples. All right, so let's look at a piecewise function. So let's make some function f of x, and we're going to say this is equal to, and then you do this little curly brace like that, and this is going to be, actually, you know what, make sure that you have enough room here. I'm going to move all this down. I have the ability to do that, so you can write on the top. I apologize if you already wrote it. You can squeeze it in somewhere, I'm sure. So this little brace, that means that we're doing piecewise, and our functions. We're going to have two functions in here. Sometimes you'll have 3 or 4, but usually 1 or 2. Usually 2 or 3. X plus 2. That's going to be when x is less than or equal to 2. And we have x squared. That's going to be when x is greater than 2. So it's the left and the right. Notice that these guys right here. Actually, I should make the arrow go the other way, so let me undo that. So these guys right here, those are the pieces. This is the left piece, so I'm going to label this this one right here left. Come on, my T and F are left piece. And then this bottom one down here is going to be right piece. And this, I'm going to do this in a different color because it's kind of important. This point, technically it's both these points. That is going to be called the suspect point. That's the one we're going to be testing for. So both of these guys, we'll make arrows to them. Both of those are the suspect point. On the homework, I talk about the suspect point. Now you know what I'm talking about. All right, so again, what is the general rule? We need the left to equal the right to equal the point. So I can even write that again down here if I need to. So the left limit needs to equal the right limit, which needs to equal the point. And to translate, I'm going to use this limit notation from the top. So what is the limit as I go to the left? How do I write that out? That is the limit. Actually, I should use a different color, but whatever. The limit of that function f of x that I just wrote up here, remember this is f of x, as x approaches my suspect point. My suspect point is now 2. All right, and from the left means I have a little negative here. What is that equal to? Well, as I approach from the left, literally you plug in the value on the left-hand side. So on the left-hand side, when I'm not quite at 2, I'm going to be talking about this function here. This is left of 2, so it's going to be at, I'm going to plug in 2 plus 2, that's going to be 4. All right, and I just did the left. Now let's look at the right. So the translation is up here, the limit of f of x as I approach that point from the right. So limit of f of x, there we go, as x approaches that suspect point. The suspect point is 2. Now from the right-hand side, and what is that going to be? Now I'm talking about the bottom function because this is on the right-hand side, the right piece, and I'm using this function, x squared. So x squared, plugging in 2, I get 4. All right, so far so good. The left does equal the right. And now how do I do the point? That's just f of that suspect point. So f of 2. And what is f of 2? Well, where is it equal to? It's equal to right here. So that means I'm plugging into the top again. When I plug in 2, 2 plus 2 is 4. This equals 4. Notice that the left, right, and point are all the same. Therefore, we can say this below. And I'm going to write this as a sentence. F of x is continuous at x equals 2, and thus continuous everywhere. Alright, so that ends the lesson. So make sure that you do your summary at the end, a few bullet points on what we did, and then you can go ahead and get started on the worksheet.